Hello, statistics and pre-calculus. Today we are going to be starting our lesson on 5.4, graphing polynomial functions. And the first thing we're going to do is go over how to investigate the end behavior of some common polynomial graphs. But before we do all of that, we have to ask ourselves a simple question of what are polynomials and what do they look like? So, whether you know it or not, you've come in contact with polynomials before. Linear functions and quadratic functions are both types of polynomials, but the standard form of a polynomial looks something like this. So, each expression that is separated by this plus sign is what we call a term. And within a term, you have x raised to some power, and you have a variable that you're multiplying x by. That variable, signified by a here, is what we call a coefficient. Now, the important thing to note about standard form is that your terms are ordered so that your highest exponent is your first term, and then we go down from there. So if you wanted an example of what this would look like, perhaps you have a polynomial function that is f of x equals x to the fourth plus 16x to the third plus 7x squared plus 8x plus 1. So note that we go from 4 to 3 to 2 to 1 to x raised to the 0, which of course is just 1, so we just have the coefficient by itself. Now, the first thing we want to ask ourselves when we are looking at how to graph polynomials is what they behave like. And within that, our first question is, what's their end behavior? So, end behavior is when we ask ourselves, what happens to my y values as x approaches positive or negative infinity? So this is actually pretty easy to do, but it's easier to do if we work through some examples together. And we're going to be looking at some pretty simple graphs today, but they can get a little bit more complicated than this. So the first polynomial we're going to look at is f of x equals x cubed. Now, if you think about it, this is in standard form. We just have what we could call a silent or an understood terms that are multiplied by 0. For example, we have plus 0 times x squared, and then plus 0 times x plus 0. Of course, all these zeros are redundant, and so what we're left with is simply x cubed. So the graph of this function looks like this. And to find the end behavior, we're simply going to ask ourselves, first, what happens as x approaches positive infinity? Well, as we move this way on the graph, our y values are getting bigger. So as x approaches positive infinity, so does y. Oop. As x approaches positive infinity, so does y. Now, in terms of the second part of our end behavior, we're simply going to ask ourselves the same question, but for negative. So as x approaches negative infinity, what happens to our y values? Well, they get increasingly more negative, or as x approaches negative infinity, y approaches negative infinity. That's the end behavior of f of x equals x cubed. So now we want to ask ourselves, what happens if we make this negative? So graphically, what happens? You should already know the answer. Okay, if you didn't guess, what happens is that we're going to reflect it over the x-axis. So we'll get a graph that looks like this. Now the end behavior changes accordingly. In fact, we have just simply flipped our end behavior. So instead of approaching positive infinity as x approaches positive infinity, our y values approach negative infinity as x approaches positive infinity, and vice versa. So we literally just reverse these two for our end behavior of our negative graph. All right, let's move on to our next graph, f of x to the fourth, which you had a little preview there when I had a technological issue. So this is the graph of x to the fourth. So as you can see, it's symmetrical about the y-axis. So this means that we're going to have the same end behavior as x approaches both positive and negative infinity. Additionally, unlike our last graph, the range here is limited to all positive numbers. So both in the positive infinity direction and negative infinity direction, what happens with our graph is that our y values actually approach positive infinity both ways. So this is what happens with the graph of f of x equals x to the fourth. Now, I want you to at least guess what you think will happen if we put a negative here. So once again, we're going to reflect it over the x-axis, which means our domain is now restricted to all negative numbers. That means that our end behavior is that our graph is going to approach negative infinity when x approaches both positive and negative infinity. Once again, we simply flipped the sign of our end behavior. This leads us to a few conclusions we can make about end behavior of polynomials as a whole. The first is that if the degree is even, the end behavior is same for both positive and negative infinity. We saw this here. As x approaches positive and negative infinity, y approached positive infinity, and vice versa for this graph. Opposite, if the degree is odd, the end behavior is opposite for positive and negative infinity, which we saw with this graph. As x approaches positive infinity, we approached positive infinity. As x approached negative, we approached negative. Our third conclusion is that if the function is multiplied by a negative constant, the end behavior is flipped. We saw here and here that was the case. All right, that wraps up this video. I will see you next time. Good job, guys.